Hi all, my name is Vishnu. I am doing my master's degree in artificial intelligence at Amartya Vishwavidyapitham, India. I am going to present the work detection of COVID-19 from chest X-ray images by deep learning approach. The entire presentation is divided into these sections: introduction, related work, method, evaluation, results, and conclusion. Introduction. In the current COVID-19 pandemic situation, there is an urgent need to properly diagnose whether people are infected by COVID-19 or not. In India, about 33 million people have been infected by COVID-19 and about 0.45 million people died. The Indian economy was affected badly by the pandemic. India's growth in the fourth quarter went down to 3.1%. Fast and accurate methods should be there to improve the efficiency of the healthcare system so that the infected people can be given priority treatment. Deep learning methods are largely incorporated in many medical fields, especially in medical diagnosis. Deep learning techniques could find patterns in images that can be attributed to various diseases. The main challenge in applying deep learning techniques in the medical field is the lack of availability of quality labeled data. Machine learning approaches such as one-shot learning methods are becoming increasingly popular in the medical community because they perform better with limited data. Problem addressed. The problem addressed in this paper is classifying chest X-ray images. It is a multi-class classification problem. Three classes are COVID-19, normal, and pneumonia. We can formalize the classification algorithm as given a sample and a label. We want to find a function f of x theta which tries to reduce the cost function based on its parameters. Our work. We compared several deep learning models for COVID image classification in this paper. State-of-the-art architectures like ResNet, AsianNet were compared. We also present a technique that combines the triplet loss and post-entropy loss functions. This technique enables the model to learn weight in such a way that it attempts to cluster different classes during classification. It will increase the model's interpretability and group together similar data. The dataset we used was made available as part of chest X-ray COVID-19 detection challenge. Related works. These are some of the key related works in this area. In the first paper, they have compared different methods to classify COVID X-ray dataset and showed that for a limited dataset, one-shot learning approach produced better results compared to other techniques. Different conventional machine learning methods were compared in the second paper. In this paper, they have used various feature extraction algorithms and used these extracted features to classify the chest X-ray. They have used feature extraction methods such as tree-level co-occurrence metrics, local directional patterns, etc. In the third paper, they have created deep learning models to classify chest X-rays. They collected datasets from Kaggle and tested the performance of various CNN architectures on this dataset. In the fourth paper, they have tried to use frog weight-based Bayesian convolutional neural networks to estimate uncertainty in deep learning solutions. In fifth paper, they have implemented a novel CNN architecture called Corodex for the classification of chest X-rays. In the last paper mentioned here, the authors have proposed a novel method based on chest X-ray classification with limited data. They refer to this as COVID-CAPS and performed well with an accuracy of 95.7%. Methods. Method. In this work, we explored various widely used deep learning approaches to address the classification challenge, including transfer learning, one-shot learning. Each of these approaches' performance is compared. We also modeled the problem as a binary classification with classes COVID and non-COVID. Transfer learning. To test this dataset, we employed some state-of-the-art CNN architectures, but we unforced all layers and trained the model so that it can better adapt to this domain. Models trained on various domains may underperform in other areas. We utilized ResNet, EfficientNet B0, and EfficientNet B7 in this work. The collected features from these networks are fed into a sequential layer comprised of several linear layers and finally a softmax layer for classifying into three classes. The loss function was categorical cross entropy, and Adam was the optimizer for this task. To control overfitting, several data augmentation techniques were performed on the training data. One-shot learning. One-shot learning is a technique for teaching models in a manner comparable to how humans learn. One-shot learning is a method for learning a new task using a small amount of supervised data and a lot of prior information. There are different approaches to solving one-shot learning problems. Mainly, they can be classified into these categories: model-based methods, metrics-based methods, generative model-based, data augmentation-based, optimization-based methods. Schematic of the model is shown in this figure. We used a Siamese network in combination with a classifier at the end of it. The Siamese part of the network tried to embed the images in such a way that to maximize the distance between samples of different classes and minimize the distance between samples of same class. After embedding the image into a latent space, we try to classify the image based on this embedded vector by passing it through some linear layers and softmax at the end of it. We have used a combination of two losses for this purpose: triplet loss function and cross entropy loss function. This allows the model to first embed the image into different clusters based on the class and then classify them better based on this embedded vector. Triplet loss is shown here. We take samples as triplets where we have an anchor image, positive image, and a negative image. Positive image is from same class as that of the anchor image, and negative image is from another class. It tries to reduce the distance between anchor and positive. Also, it tries to increase the distance between anchor and the negative image. To avoid the trivial solution, a margin term is also added. Dataset. The dataset used for this experiment is provided as part of COVID-19 Grand Challenge. The dataset consists of 22,845 images that belongs to three classes: COVID-19, pneumonia, and normal. The dataset is divided into train, validation, and test set. Sample images from the dataset is shown this figure. Experimental setup. Different image augmentation techniques are applied to avoid the model capturing unnecessary patterns in the training images. Some of the augmentation techniques used in experiments are random rotation, random zoom, horizontal flip, increasing the contrast of the images. These transformations make the model less prone to capturing features that are important or make the model overfit. Summary of the dataset split is shown in this table. Evaluation metrics. For evaluating the performance of different models, we have used following metrics: accuracy, precision, recall, F1 score, specificity, and multi-class ROC curves. Results. Table summarizes the major findings from our multi-class classification experiments with different models. From the table, we can see that efficient B7 model outperformed all others. It converged quickly to high accuracy after a proof. The Siamese network, on the other hand, was able to group together samples within the same class. Therefore, even with limited data, it would help in better interpretation and generalization. ROC curve and confusion matrix for the B7 model is shown this figure. From the confusion matrix, we can see all the samples model predicted as COVID actually belongs to COVID class, but there are some false negative, that is the model have predicted true COVID samples to be from other classes. From the confusion matrix, we can see that the model is having trouble classifying between normal and pneumonia chest X-rays. Also, the table summarizes the performance of each model on the test set based on the evaluation on the challenge leaderboard. Result: binary classification. The table summarizes the outcome of binary classification experiment. We can see that the model is nearly perfect in distinguishing COVID from non-COVID ones. The confusion matrix and ROC curve is also depicted here. Most confused samples. The figure depicts dataset most confused samples. Labels are in the order actual, predicted, loss, and probability. For the first case, normal images is predicted as pneumonia with a probability of 1 and the loss is 6.38. We can observe that the model is having difficulty distinguishing between pneumonia and regular cases. We can enhance the model's performance by classifying COVID from non-COVID cases by avoiding this problem. Conclusion. We compared several deep learning techniques for chest X-ray classification in this research. Techniques compared and proposed for chest X-ray classification in this paper are transfer learning, using campaign, triplet, and cross-entropy loss functions. All the approaches had positive results. However, rather than modeling the problem as a multi-class classification task, it would be preferable to describe it as a binary classification task. As part of future work, we would like to collect more data and improve the performance of the model and work on the quantification of uncertainty in the decision made by these machine learning techniques. Thank you.